Hello, my name is Zachary Hedges, and this is my submission for Lab 1 on constant velocity. The purpose of this lab was to compare the predicted and observed motion of an object to examine the difference in motion when velocity is constant and when there is a net force. For this lab, we assumed that velocity was constant, which means the net force is equal to 0 as there is no acceleration or deceleration. The key physics principles for this lab were Newton's second law and the momentum principle. This lab showed that there was a difference in observed and predicted motion, and there actually was a net force acting on the system. Newton's second law states that acceleration is proportional to the force exerted on an object. Momentum principle states that F net is equal to the change in momentum over the change in time. Momentum is calculated by multiplying mass by velocity, so if there is a change in velocity, there is a change in momentum, which means there is a net force. Our experiment involved a water bottle as our system, and the surroundings being a lab table. Using Tracker, I made the bottle a point mass, which allowed me to track the horizontal displacement over a small amount of time. Using Tracker, I found the time the bottle traveled and the distance it traveled. To predict the motion at a constant velocity, I needed to calculate the initial velocity of the bottle. Using Tracker, I found the position of the bottle in the first two frames. I subtracted the final position and the initial position, and then divided by the elapsed time. This gave me a velocity of 0.424 meters per second in the x direction. Using my calculated velocity and initial position, I set the initial conditions in GlowScript to generate a predicted model of motion. Delta t was equal to the time interval between each frame and tracker, which was 0.033 seconds, and the total time elapsed was 1.667 seconds. Fnet was equal to 0 due to our initial assumption. As there was no net force, velocity did not change, and position changed by initial velocity times delta t. The predicted motion shows the mass moving to the right at a constant velocity with linear displacement. Comparing this to the observed motion showed that at the end of the interval, with no net force, the bottle would have traveled farther. Had the graph continued, though, the gap between the observed and the computational position would have increased. The graph does show that there was error, as predicted motion should be greater than the observed over the whole interval. There were two main sources of error in this experiment. The first was that it was impossible to click the same spot on the water bottle each frame. This led to slight differences in the data and the true motion of the water bottle. The other main source of error is that the bottle had water in it. This could create a force inside the bottle that could rock it back and forth, causing acceleration or deceleration, which ultimately would affect the velocity of the bottle. To summarize this lab, we found that computational predictions of motion are not the same as true motion when forces are unaccounted for. Since there was a difference in the displacement, we know that velocity was not constant, and a force did act on the bottle, such as friction or air resistance.